Welcome to my video on 4-4, which is involving factoring quadratic expressions. Today we're going to focus on factoring by difference of two perfect squares and the greatest common factor. So before we get into that, I just wanted to review a question from yesterday that takes a little bit different structure. So if we look at number 85 from the textbook, it has this expression. Now, you may be tempted right away to try to expand this out and factor it. So what you might think you should do first is x plus 3, FOIL that out to get x squared plus 6x plus 9. Then you would distribute this 3 to both of these terms, to get 3x plus 9 minus 54. Okay, next, if I was going along this path, I would combine my like terms because we know that it has to be in standard form before we can factor it. So I would get x squared plus 9x plus minus 36. Okay, now that we see it, we see the structure, right? The first, it is a coefficient of x squared that's equal to 1, so we're just looking for two numbers that multiply to negative 36 and add to 9. So the numbers you're looking for here are x plus 12, x minus 3, right? Because 12 times minus 3 gives me the minus 36, and the 12 plus negative 3 gives me the positive 9. And that is a perfectly acceptable way of looking at this question. But I want to challenge your thinking to look at this from a different perspective, okay? So I want you to return to the original question. One thing you should notice right away is that we have the same binomial in a parentheses throughout the question. So we have this x plus 3. Now in this first, I'll use a different color. In this first term, right, we have that x plus 3 squared. And in the second term, we have the x plus 3 multiplied by a coefficient. And in the last term, we don't have it at all. So now I want you to think creatively. Imagine y was equal to plus 3. And that's just me imagining, right? This first term would then be y squared, right? Because we're replacing that parentheses with y. This second term would be 3 times y. And this last term would stay a minus 54. So if we just look at that, this too follows the same structure, right? Our coefficient of x squared is 1. So we are going to look for two numbers that multiply to a negative 54 and add to a positive 3. So the numbers we are looking for are y plus 9 and y minus 6. Okay, so we've are able to factor, but remember the y is equal to x plus 3. So now that we've factored it according to the rules, we should substitute the x plus 3 for y in this parentheses and the x plus 3 for y in this parentheses, bringing us to x plus 12, x minus 3. Now you'll notice both are the same, okay? Both methods work. But I want to challenge you to start looking at things in terms of structure. Do they follow the same type of structure? And yeah, in this question, even though it's x plus 3 squared, that x plus 3 is still repeating itself in the same pattern as a standard quadratic trinomial. So we're going to use that skill a little bit later on in this lesson. But first I want to focus on perfect squares. Since we're going to be factoring the difference of two perfect squares, it's important for you to be able to recognize the perfect squares that might appear in your question. So numbers like 1, 4, 9, 16, 25 are all perfect squares that you should be able to recognize as such on a question. Same thing with 36, 49, 64, 81, and 100, right? All perfect squares. Now, you're probably most familiar with those first 10. But you should also be relatively familiar with 121, 144, 169, 196, and 225. So in terms of questions, the majority of the questions you will be looking at will have that are factorable by difference of two perfect squares will have those perfect squares within the question. So it's important to be able to recognize them to be able to use this method. So as always, with any factoring lesson. We started off by multiplying because multiplying and factoring, right, are precisely opposites. They undo the other. So if I FOIL this, I have an x squared plus 2x minus 2x minus 4. Now, the wonderful thing that happens with this question is that the plus 2x and the minus 2x cancel each other out. So instead of getting a trinomial when I combine my like terms, I end up with a binomial or something with only two values. Now, what else is important about this structure? Well, if we take a look, right, this first term comes from multiplying the same value to itself, aka a perfect square. Same thing for this last term, right? It comes from multiplying the same value to itself, which is a perfect square. Now, the other key feature here that we should focus on is the fact that one is positive and one is negative, which creates this difference that we need for the difference of two perfect squares. So if you are ever presented with a question that is x squared minus 4, we should understand that the factoring presents two parentheses that look essentially the same, except one has a positive and one has a negative in between the two terms. So that's the basis behind difference of two perfect squares, right? If we have a perfect square minus another perfect square and we are asked to factor it, we get two parentheses where we essentially break it up to the base of this perfect square in the first position and the base of the second perfect square in the second position, and then we have one positive, one negative. Now, we already created a list of perfect squares, but the other thing that we have to pay attention to is the fact that variables can be perfect squares in different forms, right? X squared is a perfect square because it is equal to x times x. But we can also say that x to the fourth is a perfect square because we're multiplying x squared times x squared to get to it. Now, if we proceed down the list, x to the sixth is created by multiplying x to the third times x to the third. So there's a pattern here, right? 2, 4, 6, right? What's the next number in that list? Hopefully we recognize that would be an exponent of 8, which would be x to the fourth times x to the fourth. So it's going to turn out that any even exponent is a perfect square. And we can break it up into our factoring parentheses by essentially dividing the exponent in half to find the exponent that was multiplied to itself, right? So if we take a look at x to the fourth minus 25, well, 25 is a perfect square, x to the fourth is a perfect square, and it is a difference. So when we go to our factoring bubbles, right, remember, this first one has to be the base of x to the fourth's power. Right? So that is x squared, because if we take x squared and multiply it to itself, that's what gives us the x to the fourth. So instead of just putting an x in this first position, we're going to put an x squared. 25, right? What is the base of 25? Well, that's 5. So then we put 5 in the second position. And then, as always, we put 1 minus and 1 plus. Now, it does not matter which order you put that in, as long as it is the 5 that is being applied, as long as it's the 5 that has the negative sign. All right, so that would be the final answer here. The other thing we need to remember about difference of two perfect squares is that it can include terms that have a combination of variables and coefficients. So here we have a 9 as our coefficient. It is vital that that coefficient is a perfect square as well, right? Because in order to get that first term, we need to multiply the same thing. So what is the base of 9y squared in terms of this difference of two perfect squares structure? Well, that's going to be a 3y. Because if you remember properties of exponents, right, if you have it inside of a parentheses and you are raising it to the exponent, each one of those things gets a copy of the exponent. So 3 squared gives me the 9, and y squared gives me the y squared. So when I break this up, I get 3y plus 4 and 3y minus 4 as our final answer. And again, you could switch those two parentheses due to the commutative property. So now let's apply this to some more challenging examples. Okay, now I want you to pay attention to this direction right here. Factor completely. All right, factor completely means that you are factoring until every single parentheses can no longer be factored. All right, so once you have used one factoring technique, you always reapproach each parentheses and see if there's any other factoring technique that can be done. So for example, x to the fourth minus 16. Hopefully you recognize x to the fourth is a perfect square and 16 is a perfect square. So the first step in factoring this would be x squared plus 4. X squared minus 4. Now, because x squared, right, is a perfect square, and 4 is a perfect square, it should really be screaming at you off the page. Factor me, factor me, factor me. Now, things to remember. There is no such thing as sum of two perfect squares. Okay? No such thing. Okay? Because we need that change of sign to create that canceling out effect. So the sum of two perfect squares cannot be factored. So this first parenthesis of x squared plus 4 simply just follows us down to the next line. However, the second parenthesis here of x squared minus 4 is a difference of two perfect squares, as we saw with our first example. And we can factor that to x plus 2, x minus 2. Okay, so now x squared plus 4 cannot be factored, x plus 2 cannot be factored, and x minus 2 cannot be factored. So there we have an expression that has been factored completely. Okay, so let's try number 2. Number 2 is different from the other questions because there's multiple variables. Okay, but again, as we said, if coefficients are perfect squares and variables are perfect squares, it still together as a whole becomes a perfect square. So this particular example can be factored as 6xy, because that is the base, plus 1, because 1 is a perfect square, and 6xy minus 1. Now, nothing there, although the 1 is still a perfect square, the 6xy cannot be factored any further. So there we have our final answer. So it works with multiple variables as well. Number 3. So number 3, what's the difference in the structure? Because that's what we're looking at with factoring. Well, as opposed to the first two examples, the number 81 is before the variable y to the 8th. So what's key about this type of question when the order seems to be switched is that you must mimic the order that you see in the question in your difference of two perfect squares factoring. Okay, so if 81 is in the first position, then when I factor it using difference of two perfect squares, the 9 must be in the first position in both parentheses. Now, why is that key? Well, remember, this negative is in front of the y to the 8th. So the negative within the question has to be in front of the y variable. Okay, so now if we continue looking, is this factored completely? Well, we know 9 plus y to the 4th cannot be factored completely, cannot be factored further. But 9 minus y to the 4th can be factored to 3 plus y squared and 3 minus y squared. Now, although we have some higher exponents, right, sum of two perfect squares doesn't work, and 3 is not a perfect square, so there we have our final answer. Okay, now remember, commutative property says anything with the plus in between can be switched order. So if you are somebody who likes to have your variable in standard position, you could rewrite this in this format. However, when you get to the parentheses with a minus, okay, it should follow the y when you switch the order. Okay, so last but not least, question number 4, 36p to the 6th minus 81y to the 8th. It may be tempting to say, oh, 36 perfect square, p to the 6th, 81, y to the 8th, and to go directly to 6p to the 3rd plus 4p to the 4th, not 4, I apologize, 9p to the 4th, and 6p to the 3rd minus 9p to the 4th. Okay, very tempting, but hopefully you should recognize that the 6 and the 9 in both parentheses have something in common. Right? They have a common 3. So in theory, we can factor out a 3 from both parentheses to get 2p to the 3rd plus 3p to the 4th. And do the same for the second parentheses. 3, 2p to the 3rd minus 3p to the 4th. And now we have two 3's on the outside, which we can combine to get 2p to the 3rd plus 3p to the 4th. Oh, I'm sorry. I messed up a little bit here. This p should be y across the board. Y, 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 and y. Okay, and then 2p to the 3rd plus 3y to the 4th. Okay, which is finally our factored completely format. Now, if you take a look at the original question, you might have noticed that both of those values are divisible by 9. So you could have easily factored out the 9 first to get 4p to the 6th minus 9y to the 8th, and then use difference of two perfect squares, recognizing that those were all perfect squares. And you would get to the same answer, right? 3y to the 4th and 2p third minus 3y to the 4th, right? Those are the same. Okay, now I'm going to encourage that you find your GCF first, okay? Because in a lot of cases, by factoring out the GCF first, either A, you can factor out, you can find new methods of factoring, or B, you might see that it's not factorable at all. For example, 2x squared minus 16 is awfully tempting to use difference of two perfect squares because we have an x squared and a 16, both of which are perfect squares. But that 2 being a coefficient does not allow us to use that format, right? But we do recognize that the 2 and the 16 have a common 2. So I can factor out the 2 and get x squared minus 8. Now, if we look at that, we might again be tempted to do the difference of two perfect squares. But by factoring out the 2, we should be able to recognize that 8 is not a perfect square. So although we were able to factor out a GCF, that's as far as we can go. Okay? So greatest common factor is a very important tool in our factoring toolbox. And essentially what we are doing is factoring out the largest factor that is common to all of our terms. So that includes coefficients and variables. So looking at the first example, first I look at my coefficients, 18, 63, and 9. What do all of those numbers have in common? And that is a 9. But I also need to look at the p-values. What is in common in terms of the p's to all of those terms? And that is just a single p, right? Because if I take a single p out of that last term, there's nothing left for me to factor. All right, so my GCF is 9p, leaving me with, inside my parentheses, 2p squared minus 7p minus 1. All right, so that's our greatest common factor. What about the second values? What's our greatest common factor there? Well, 2, 3, and 4 have nothing in common, right? It has to be in common to all of them. But they do have a common c to the 3rd power. Now, if I factor out c to the 3rd, I am left with 2c squared d to the 4th minus 3c plus 4. Okay, and so there we have the greatest common factor. Now, there's one other type of greatest common factor that we have to look at. Okay, and it's not going to look very similar to anything we've seen before. Okay, so we have 5y times y plus 3 minus 2 times y plus 3. Now, if you remember in the do now, right, we treated these grouped parentheses almost as if it was its own variable, right? We said let y is equal to x plus 3 in our first example. All right, so using that same idea, if we look at this as its own parentheses, okay, this y plus 3 parentheses, it is a common factor because it's being multiplied to both of those terms. So if I factor out y plus 3 from both terms, what am I left over with? Well, I took out the y plus 3, and I'm left with a 5y from the first term. And I took out a y plus 3, and I'm left with a 2 from the second term. That being said, I now have two parentheses that are factored completely. So that's called a common binomial. And that is a skill that we're going to apply later on to other methods of factoring. So you can factor out a common coefficient, you can factor out a common variable, and you can factor out a common binomial. So let's look at two more examples just to reinforce that. What is our common binomial here? Well, x plus 8 is in common to both of those parentheses, both of those terms. So if I factor out the x plus 8, I am then left over with x plus, and now we don't see a 1, but hopefully we know there's a 1, plus 1 in our second parentheses. Okay, so again, for the second one, what is our common binomial here? Well, x minus 5 is common to both of those terms. But what is left over? X squared minus 4. Okay, now remember, we are factoring completely. So just to tie it in with what we did earlier, we have factored out our greatest common factor, which turns out to be a common binomial. But we can also factor using the difference of two perfect squares of x plus 2, x minus 2. All right, so there we have it, factored completely with nothing left that can be done. Okay, so what I'm going to ask for you to do for homework is on page 221-2 through 222, and it's these following numbers, number 72 being a challenge question.